Okay, now discuss our next problem. So this is related to rainbow. So this problem, so let me write. So you can see this problem is formation of rainbow. Now what we have, so let us first draw the diagram. We have A. So here I have a diagram. So this is a raindrop. Now I have one normal going something like this, another normal that is goes something like this. So you have to make the diagram, and one normal is something like this. So let us say if a light ray is incident at this point and angle of incident is given, so this is, let us say, theta. So this point is A. Now this point of angle of incidence is, so this is theta A at point A. So let us call this angle as theta A at point A. Now this light rays goes in this way and it touches here. So this is my light ray. Now at this point this angle is called theta A at B. So this angle is, basically they are calling this angle is theta B at A. Now this angle is called theta A, and then let us call this point is point B. So this angle is calling theta A at B. Now after reflection, this is the total internal reflection, they are calling this angle is theta B at B. Now this angle is again, so this point is C. This angle is called theta A at C. Now finally light ray again deviates from the normal, so it goes something like this. Of course this is not horizontal. This angle is again called theta B at C. So these are the diagrams that is given. So if angle is incident any point coming at that point, we call it as subscript A. If it is going, we call it subscript B. And now if at point A, we will simply write A, and if it's like theta A and A. If it going from point B, we will call it theta B at B. If it is coming at point B, we will call it theta B at B. Now the first point, so let us read the question. A rainbow is produced by reflection of sunlight by a spherical drop of water in the air. So this is a spherical drop of water in the air. This figure shows a ray that reflects into drop at A. So first point, it refracts at A and is reflected from back surface of the drop at B. So this first refracts here, and then it reflected here and refracts back into the air at C, and again refraction. So we have reflection, refraction, reflection, and then refraction. So 3 times. This is basically total internal reflection. So 2 reflection, 2 refraction, and 1 reflection. The angle of incidence and refraction are theta A and theta B are shown at point A, B, C. And the angle of incidence and reflection theta A and theta are shown at point B, so that, so these the angles are shown, so that the first is, so you have to prove first point, that is theta A at B is same as theta B at A. This is the first thing. Then you have to show theta A at C is same as theta B at A. And then again you have to show theta B at C is same as theta A at A. Now things are easy. If we proceed further, so if you see now theta B at A, so theta A at A, so this angle theta A at B, so this is theta A at B is same as theta B at A, so theta B at A. So this is obvious because this is a radius, this is also a radius. So if this triangle, these are the equal sides, so angle on the base should be equal. So if I say angle on the base, angle on base should be equal, and that is the case theta A is equals to theta B. So this is the obvious, the first part. Now you have to prove theta AC is equals to theta AC, theta A at C, so C, and this is the theta A. So theta A at C is same as theta B at A. So theta B at A. So this angle is theta. So now you see this angle should be equals to, so I can say theta, because the again triangle. So you have a triangle with equal sides, two equal sides. So I can say theta A at C is equals to, so theta A at C is equals to theta B at B. And we also know, now if I know theta B at B, because this is the reflection, so if I apply, so this is from triangle, so this result is coming from triangle. Now this is A, B, C, let us call this O. So this is coming from triangle BOC. So this is coming from triangle BOC. Now if I apply reflection, so property of reflection, and the reflection says angle should be equal, so theta A at B is same as theta B at B, because this is a reflection, so at reflection angle should be equal. So this means theta B at B is same as theta A at B. So if I write, so if I, let us say the equation 1, this is equation 2. If I combine equation 1 and equation 2, I can write theta A at C is same as theta A at B. Now I have to write theta B at A. So now if I combine again, so this is theta, so let us say this equation is, this is equation X. So if I use equation X, theta AB is same as theta BA. So this is again theta AC is same as theta B at A. So now we have proved the second result. Now the third result, theta B at C is same as theta A at C. So theta B at C is same as theta A at C. How can we prove? Now these angles are equal, so now we have proved this is equals to this and this is equals to, so this angle is equals to this angle, because the basis, you see we have proved this angle is equals to this angle and this angle is equals to this angle because reflection, and then this angle is equals to this angle. So now I can prove this angle is equals to this angle. How we can prove? If I write the law of Snell's law at point A, I can write, let us say this side medium as refractive index 1 into sin theta A at A is equals to n times sin theta B at A. So this is if I write at point B. Now if I write at C, I can again write n times theta sin theta A at C is same as 1 times sin theta B at C. Now you see these things, so if I see here, we have already proved theta B at A is equals to theta A at C. So theta B at A is same as theta A at C. So theta B at A is same as theta A at C. So these two things are equal. You see from here I can say theta A at C is theta B at A. So these two things are equal. So now if I combine these two equations, I can write sin theta A at A is same as sin theta B at C. So this means now I can say theta A at A is equals to theta B at C. So this is the result we can always write. Now this is the first part, this is the easy part. Now the second part says, so that angle in radians between the ray before it enters the drop at A and after it exit at C, the total angular deflection is given by. So you have to prove total angular deflection is given by 2 theta A at A minus 4 theta B at, this is at A, plus pi. So we have to write in terms of theta A. Now what we will do is we will find what are the reflection at the all faces and then we'll add simply. So you see at the first face what is the reflection? What is the reflection or deviation at the first face? You see at the first face here. So let me see. So if you see the first face, this is the theta angle and the final angle is theta b. So you can see this angle has basically, if this goes something like this, so this angle will be theta a, but now angle is theta b. So the angle of deflection is theta a minus theta b. So I can write at point A, deflection is theta a minus theta b. Now what is the deviation at point B? So let us find deviation at point B and then we will add all this deviation. Now this light ray is going this side, but now this is going this side. So what is the angle? So this angle is pi minus these two angles. So pi minus this angle is basically equal. So pi minus 2 times theta a at B. I can write, so theta a at B or theta b at B is same. So let us write pi minus 2 times theta a at B. So I can write this angle is pi minus theta a at B. This is at A. Now I can also write delta C. What will be the value of delta C? So let us see again. If you see here, delta C will be, this is the theta b at C and this is the theta a at C. So angle of deflection is how much? So this ray should go something like this, but it is basically going through this. So angle of deflection is, so this angle is theta a at C. So this angle is theta a at C and this angle is so this angle is theta a at C. This angle is theta a at C and this angle is theta b at C. So theta b at C minus theta a at C. So theta b at C minus theta a at C. This is the basically deflection at each point of deviation. So total deviation is delta 1 plus delta 2 plus delta 3. Now basically all angles are you can say, so theta a at A and theta a at A. So let me write, so I need 4 times theta b of A. So theta b of A 1 times. Okay, so delta will be so total is theta, so pi plus I will have theta, I need theta a at A 2 times. So theta a at A here I have, and then I should have theta a at A, this angle. So theta b at C, and now you see, so theta b at C, you see your copy, you will find theta b at, so this angle, so you see theta b at C. So this is C. So theta b at C is same as theta a at A. We have already proved. So this is basically, now I can say 2 times, this is plus 2 times theta a at A. Now these 3 angles are basically equal. So I should get one more time because I have 4 times theta b at A. So should I get one more theta? Where should I get? This is, oh okay, good. So theta delta b is basically 2 times theta a at B. So you see here, so this angle is 2 times theta a at B. So deflection is delta pi minus, so this is 2 times theta, so this is total. Now these all angles are equal. So here we have already proved these all theta b at A, theta, so these all angles are equal. So I can write 4 times theta b at A. Are you getting or not? I can write in any angle because we have proved, so these are our internal angles. We have already proved these all internal angles are equal. This angle, this angle, this angle and this angle. So if I have theta a b at A or theta a at B or theta b at B, theta a at C, all are equal. So this we have already proved. Now the total deflection is given by this principle. Now you see theta A we know, and then we can find theta B using the sine rule. So theta B we can find. So if I apply sine rule here, theta B is nothing but sine theta A by n inverse. So I can write theta B at A is nothing but sine inverse, are you getting or not? Sine inverse sine theta A at A, sine theta A at A by n. So this is the my theta B. So total deflection is given by pi plus 2 theta A at A minus 4 times sine inverse sine theta A at A by n. Now the third part says, this is the important part, a rainbow will be formed when the angular deflection delta is stationary with respect to incident angle theta A at A. That is when delta d delta by d theta A at A is equals to 0. So rainbow is formed when this delta remains constant with respect to theta. So to find the theta 1, what we can do is we can differentiate this equation, and so let us take a special case. This maxima occurs when theta A at A is equals to theta 1. So this is the point when the maxima occurs. So you differentiate this equation and prove that. So you will have a solution of theta 1 is something like this. Cos square theta 1 is equals to 1 by 3 n square minus 1. And this part is easy. You can just differentiate of sine inverse and you will find the answer. We have already done. If you want, we can do once again. So if you differentiate this function, you can do yourself. There is nothing hi-fi. It's simply mathematics. If you differentiate this one, so d delta by d theta 1. Now this theta 1a, this is theta a at a. I am differentiating with respect to, so pi will 0, and differentiation of this is 2 minus 4. Sine inverse will be 1 by 1 minus x square sine theta a at a by n square, and then you will have differentiation of sine theta, that is cos theta a at a. Now if you see, this is equals to 0. Now this is total mathematics. So you will have root over 1 minus sine theta a by n square. This is also a square because sine of a square we have, differentiation is equals to 2 times cos theta a at a. Now let us say this maxima occurs when theta a at a is equals to theta 1. So I can have a solution for theta 1 also. So you see, if I square both sides, 1 minus sine theta 1 whole square, this is n square already we have, by n square is equals to, so 2 becomes 4 cos square theta 1. Now so I can write, so this is n square minus sine square theta 1, this is equals to 4n square cos square theta 1. Now you see, you have to have in terms of cos square theta. Okay, so there is one term missing. If I am differentiating this one, so sine inverse, if I am differentiating this sine inverse, I will have 1 by 1 minus x square. So 1 by 1 minus x square, and then differentiation of this is 1 by n also. So I have to multiply 1 by n here, and then we will have 2 by n here. Then I will have 4 by n square here. So this n square goes. So I will have n square equals to 4 cos square theta plus sin square theta. So sin square theta plus cos square theta becomes 1. So we will have n square minus 1. This is equals to 3 cos square theta. So cos theta is simply given by n square minus 1 by 3 under root. So this is the value I will get. So this you have to prove. Now the index of refraction of violet light of water is this. So for refractive index for violet light is 1.342. Refractive index for red light is 1.330. You have to find what will be the theta for these lights. So cos theta for violet light you will have, this is 1.342 whole square minus 1 by 3. For red light you will have cos theta red is equals to 1.330 whole square minus 1 by 3. So you see, for different light you will have different cos theta. So similarly you can, so this means a ray that is going white here. Now after refraction and reflection and then reflection, you will have different rays because you are having different thetas. So this is the basic principle behind the rainbow. So the important point you have to see in rainbow, all the internal angles are equal and incident angle and final refracted angle is again equal, and the point is delta for different rays depends upon refractive index, and the final equation says. And another point is we can find total delta by adding delta 1, delta 2, delta 3. In case of delta 1, this is simply theta 1 minus theta 2. In delta 3 is again theta 1 minus theta 2. But the delta 2 is pi minus theta 1 plus theta 2. That is theta 1 and theta 2 are equal. So, and then we have to see the another point that is important. So we get the rainbow only when this delta becomes constant for a given theta. So this means we will not get delta, a stationary delta for all theta. So the delta keeps changing if I change the theta, but there is a delta that will give a theta that is constant, and corresponding to that theta we will have the rainbow for that particular light. For violet we will have particular dispersion delta. Similarly we will have particular dispersion for different light. So this is the basic principle behind the rainbow. Okay, maybe you will find this video quality somewhere difficult because the problem of light sometime we have, sometime we not have. Okay, we'll discuss the next problem.